Hello. Hello. Is there anyone who is asking something? Okay. So, as we know,
Ma'am, you are on mute.
Madam, we are unable to hear your voice.
so from when I am on a mute from the first slide.
Now it's okay, madam. Now it's okay. Only last 20 seconds we are on mute.
Okay. Okay. So, as we know, what are medical imaging? These are just radiology or medical imaging. We can also say that this is just a radiology. And in the field of medical imaging, why we are getting these? We are just getting these for identifying the internal structure of a body. If there is some problem inside the body, we can just get the medical imaging, and then we can see that what are the problems inside your body. So basically, there are different medical imaging modalities which are available. That is MRI, which we even call it as a magnetic resonance imaging, and CT image is there. That is computed tomography. Then other is ultrasound imaging. Then positron emission tomography. That is called a PET imaging. Okay, which are basically related to the nuclear imaging, and other one is your positron emission mammography, and many more are there. So basically, this is just an image on the, you can see the MRI image of the human head is there. Okay, this is the MRI image of head, and this is the CT scan image, and this is just a PET scan, and this is your ultrasound image of the kidney. Okay, you can see that there is a kidney stone inside it. So basically, these are just the medical imaging modalities. So now we know that what is medical imaging. So as we say, we need to identify some problem. If we need to identify some problem in our body, so we need to have some medical imaging. Okay, so for our body. So once we are having a medical imaging, then obviously we need to find the exact what problem is there in our body. Okay, so for that we need some, that is image segmentation. Okay, methodology. So basically, what is this image segmentation? Okay, it is just converting your image into a collection of region of pixels, okay, that belong to the same object class. Okay, or you can even say different clusters you are going to make of your particular image which belongs to different objects. Okay, so like here, this is just the image or the example. Okay, in this image, you can see that it is a image of a street where buildings are there on the both the side. Okay, so buildings are there, so that is belongs to one object class, that is a building. Then car are there, so it belongs to the other object class. So therefore, it is given different color. Like street, like road is there. Okay, so it is given a different color. And here, other one is like a human body. Okay, that is the humans, so they have categorized into a different class like human. And if trees are there, a tree for them also, it is like green color allotted to that. Okay, so this is just the image segmentation. And now what are basically the application of it. And in medical imaging, it is having the very big application, as in the previous slide you have seen. In the ultrasound image, there is a kidney stone present in that. Okay, so you need to find out the region of that stone. So that is, or you can even want to find out that where exactly some person is having a brain tumor. Okay, so doctors want to find out that the size and the region of that brain tumor so that they can remove it from the head. Okay, so and like you can even have that, find out that affected region in your lung due to lung disease, like COVID-19 is going on. Okay, for example, someone want to find out that how much your lung is affected by a disease. Okay, so in that, It is very beneficial. And as we see, is it clear here? So now that is medical image segmentation. As I said that we are just finding out the problem inside the body, that is identifying the pixels of organ or the lesions from medical images such as CT or MRI. Okay, and basically it just help in delivering critical information about the shape and volume of these organs. Okay, that is that how much the size of your tumor and all those things. So earlier what happened is that what we, in case of image segmentation, people used to make use of edge detection methodology, thresholding methods, morphological operations. Okay, all these are related to the mathematical models. Okay, so they use these kind of methods in order to perform the image segmentation task, like normal thresholding operation they use. So after that, the normal, these kind of methods, there comes the machine learning methods. Okay, where you provide some set of features that tumor look like this. Okay, so if this kind of shape is present, then find out this kind of shape. For example, tumor is, let's say this shape is just like a circular, it is in a circular form, just an example. So what it will do, it will just identify, just take the feature of that shape, give to the classifier, and then on the basis of that it will just find out that region. Okay, so these are just the machine learning approaches. Thereafter there comes the deep learning methods. Okay, and we know that everyone now have started using deep learning in medical imaging as well. Okay, uh, so just see, look at this example here. This image shows the segmentation example. Okay, where this image is segmented into three different regions. Okay, based on the color intensity values. Like here white color, there is something, then if it is like light pink color, and here light blue color. Okay, these are just the nucleus in the right hand side. These are just the blood or the muscles which are present in your body, and these are some water content level. So this is just the segmentation. Okay, so now let's talk about classification. So what exactly it is? As we know, whenever we want to categorize something into different categories, that we call it as a classification, or we can even say it is the process of predicting the class of given data points. Okay, and classes are, even you can call them as the categories, or you can target or the labels. So what is basically, let's say, take an example of a person is having a cancer or not a cancer. Okay. So for example, you have two different categories, that these are the images which belongs to the normal patient, and some set of category of the images which belong to the tumor cases. Okay, let's say tumor and normal. So these are two different categories we people are having. So this is what, if someone new patient have come into the hospital and they want to find out whether this person is having a tumor or not. So in that case, means we are categorizing that human, that is the new patient, into one of these two categories. That is whether a tumor or a not a tumor. So this is called a classification. Okay. So earlier, what people used to do in case of classification, they take the images of the, let's say this is the brain image, for example, let's say they take, then they perform some kind of pre-processing operations on that. For example, they are performing the image enhancement. Okay, increasing or decreasing the contrast of an image. Okay, then after that, image segmentation they can apply. It is not an mandatory that for classification you have to apply this segmentation. Okay, let's say image segmentation we are applying. So in case of brain here, what we can do in case of segmentation, we can remove the skull part from the MR scan or CT scan image. Okay, then after that, performing the segmentation features, they will use to extract features, and then based on the features, the particular person will be classified into the category of tumor or a non-tumor region. Okay, this is what earlier people used to do. Okay, Now, nowadays, what people are doing, okay, because they have started using uh, deep neural network. Okay, we can always say that a convolutional neural network as well, deep learning. Okay, so they've started using this deep learning concept. So what they do, they take just an imaging. Okay, they are not performing any kind of image pre-processing, any kind of segmentation. What they are doing, just taking the image and then just performing the convolution operation, max pooling operation, and then many more operations which are related to your deep learning. Okay, and then on the basis of the final layer, that is, there is a fully connected layer, and they extract the features along with the clinical information. Okay, this is an optional. If you want to take, then people can take this information as the one of the, you can say, it will just improve the result. If you are taking the clinical information, that is, let's say in case of tumor, it can be like, clinical feature can be like, since how long he is having the headache in his okay, brain, so, or something like that, and what are the molecular features, histological features, and the treatment information. Okay,
I think it got stuck.
actually, sir, light is not there. I am connecting with my phone just now. Oh wait, actually, there is some problem related to the light. I'm sharing once again. Now is it visible?
Yes, ma'am.
Okay, thank you. So my, I'm closing my video as I have connected with my phone. So, so now here, As we are talking that in classification nowadays people are started using deep learning methods. So basically they are just extracting the feature. They don't have to perform any kind of pre-processing, segmentation or these kind of operations. So they can directly uh, use these deep learning layers, that is convolutional layers, pooling layers and fully connected layers, and on the basis of that they are extracting the features. And if you want to take the clinical feature, clinical information, then you can also take that information and can find out what exactly the problem, or you can just categorize them. So this is just people which have started using this, not a normal machine learning methods. Okay, so now what are basically the challenges which are related to here this medical imaging? So first and the most important challenge is that the rarity of medical imaging data set. As we know, for example, you have taken some topic that on this work you have to do the PhD thesis or something new you want to do. So in that case you will not be able to find the data set. Then for that you have to collect it from the hospital, from the clinics and all those, and it is a very difficult task to collect the data. And there is also a problem which is related to the annotation. Okay, means that for example you have collected the data, now you have to also find out that where exactly the problem is. Let's say the example here it is given, the skin example, melanoma. Okay, so this is the type of skin cancer. You can see here one picture is also shown here, that the different type of skin cancer like squamous cell carcinoma, basal cell carcinoma and melanoma. So melanoma means when it reached here into the dermis. Okay, so this is just say the example you are having. So now as a human you can see that this is the reason where the problem exists. Okay, so you can mark the ground truth. But let's say in case of brain tumor and something there, so how will you identify that where exactly the problem is? Okay, so for that you need the doctors, and doctors are very, they don't give time. Even I have faced the experience during my PhD. I faced that they don't have time to do the annotations. The other one is the organ appearance. Say here in this case here the person is having a light skin, so melanoma can appear here very clearly. Now let's say people who is having a dark shade, so in that case it is very difficult that to distinguish between basal cell carcinoma and melanoma. So challenges are also appear related to the organ appearance on the human body, and the quality of the data is also the challenge. That let's say this is a taken image of 250 cross 250, maybe other images of other dimension. Okay, and the other challenge is that is the regular meeting with the medical experts and overfitting of your data. When you are going to train with the less data, then it will give you the overfitting, it will not give you the exact results which actually you want. And let's say you are having a more data with you, then in that case training time will be more. Okay, and on your normal machine you are not even able to perform the image segmentation on the classification, as it will take more time, and for that you need to have some that is called a GPU, okay, instead of CPU. So these are some of the image analysis tools which are available, and currently doctors are using these tools. Okay, the first is the AMID, that is a medical image data analysis tool. So this is available. Then next is your FSL. Okay, this is just for fMRI images. If you are having the fMRI images, then with this tool you can analyze those images. ImageJ is there. Okay, ITK snap. So this image what I have shown here, that is the taken from the ITK snapshot. Okay, that is ITK snap toolbox. So here in this case, you can just easily visualize where exactly the tumor region is, okay, and how much where it is spreading and how much region. Okay, red is just showing the core of your tumor. So this is just the example that with these tools you can visualize your medical data. Okay, MITK is also there. So the medical imaging interaction toolkit and OSIRIX. Okay, this is basically just for DICOM images. If you are having DICOM images, you want to visualize it, then you can use this Osirix. Okay, the other one is your 3D slicer. So it is just also like a ITK snap as shown here, this image of brain tumor. So it will just provide you the perfect visualization, whether it is in the 2D or 3D. It will with the help of these tools you can visualize your medical data. Okay, so some of the data sets which you can use for your research work are MedPix. Okay, it is just a free open access online database. That is, other is the Cancer Imaging Archive. So this is also the data to means repository from where you can download various imaging data. Okay, the other one is V7 COVID-19 X-ray dataset. From here you can download that. OSS brain dataset is there. MRNet, that is knee MRI data, structured analysis of the data of retina. So STARE database is there if you want to work on the retina. Then MURISE, that is MSK X-ray images are there, which is related to your knees. And then there is Che export. It is also related to your chest X-ray images. Okay, so various like Kaggle, UCI, machine learning repository, Grand Challenge. These are the various data set also and the repository from where you can download your data set. So just see here. This is a grandchallenge.org, and inside it you can find various challenges. Okay, just you have to click on challenges and you can find the various challenges which are currently going on, and you can participate in them. See here, they are written as PARS 2022, means these are the challenges which are currently going on, and if you want to take participate in this, you can just uh, take out that data whatever they have given, just perform the algorithm what you are going to design. Okay, and just take out the result and you can submit your result to these, okay, to these challenges, and they will verify that whatever input or results you have taken out, whether they are matching with the ground truth or not. That is, means in case of training data, they are giving you the both the ground truth information as well as images. But for the testing data, they are not giving you the ground truth information. They are checking the ground truth with the results which you are having obtaining. Okay, so on the basis, so you can just find out that what are the basic, okay, that data sets which you want to use. Okay, so like here, PARS is generally for preliminary artery structure. The other one is endoscopy artifact. The other one is your colon nuclei identification. Then other one is your, this is AROX, is for robust glycoma screening challenge. Okay. So now, as we have seen, what are the application means data sets and what are the tools. So now let's say the conventional methods. What are there? So basically, in earlier time, people used to just perform if they want to do the segmentation or any kind of task. So they, what they do, they just perform the thresholding operations. Okay, they take the input image, and then on the basis of that input image, they generate their histogram. Okay, and then they find out one of the threshold value, and on the basis of that threshold value, they are just partitioning, or they are just partitioning the image into two different category. Let's say one is the category belongs to the object and one category is the background. Okay, so like here, the white region is showing you the foreground images and black is your background. Okay, so these are just conventional method. And other than thresholding, there are also the people have used edge based method, like this is the MRI image. Okay, and on right hand side you can see the boundary regions. Okay, the brain structure, how it is. So it is just by the canny edge detection methods which people have used. These are not just a one, like canny can be the Privet method, it can be your Sobel. So these are just normal the edge detection based method. So in conventionally, earlier people used to make use of these like watershed methods, like these are the basins, okay, minima, and so it will just this is just the method which people have even used. Then hard and fuzzy clustering techniques. Okay, just like the fuzzy clustering, like FC mean clustering, k-mean clustering. Okay, so in that case, what they have to do, they have to find, just as an input, they have to give that how many clusters, in how many clusters you want to divide your image. Let's say they want to divide an image into two category, or let's gray and white. So on the basis of that, these are just the methods. So why we have come from conventional methods to deep learning method? So the one is that deep learning methods give you more accurate results. Okay, and automatic features extraction is there. You don't have to give the features. Okay, otherwise in conventional method you have to perform the pre-processing, segmentation, then you are going to find out the features, and then you are giving those features to the machine learning models. Okay, so those steps are not needed here. You can just machine learn, these deep learning methods will just take out the automatic features, okay, automatically, and will just perform the task whatever we have decided for those methods. And it can handle your unstructured data. So basically machine learning models are just for structured data, means you are having the features which are in the form of tabular format. Okay, like vector 1, vector 2, vector 3. Okay, and those information in the form of vectors you are supplying to your machine learning bot. But here in this case it is working on unstructured data, means you can work on the images, you can directly work on the videos, you don't have to find out the features. So that is why we have moved from normal conventional machine learning models to your deep learning models. Okay, and some of the most commonly used machine learning models which we are going to discuss now is that this LXNet architecture. From this LXNet, this is just the model name, which is designed by Krzyzewski in 2012. Okay, this is just, they have designed for the ImageNet classification of their data, where they are classifying their 1000 category. Okay, by using this model. So, and I think in the previous note you already have the information about that. That is, they are taking the input image, okay, which is of size 224 cross 224, and 3 means that it is an RGB image, that is red, green and blue component. And like here you can see 48 and 48. So what basically, these are just your number of filters which you are using. So here number of filters, or you can even say kernels, how many kernels you are using. So as at that time in 2012 they don't have that powerful GPU, so they have run their algorithm on 2 different machines. Therefore you can see here half part is missing here, so they haven't put this half part. Okay, so directly I have taken that image from there. So like these and then they are performing the max pooling operation, that is after convolution. This is just a convolution operation from 224 to, it has become the size to 55 cross 55. Okay, then again they are getting the information, and finally you will get that in how many categories you want to divide. Okay, you want to find out that to which category that particular thing belongs. So this is just the basic architecture of LXNet. So but in case of medical imaging, if you want to perform the segmentation, okay, you cannot do with this. Okay, just see here, it is every time it is decreasing the size of your image. Earlier it was 224 to 124, then its size reduced to 55 cross 55, then 27 cross 27, then 13 cross 13, likewise. Okay, every time we are decreasing. But in case of segmentation, what we need, whatever image we are having, we want the same thing, okay, same size image in the segmentation result. For example, tumor is there in the brain region, so obviously the same size on the same size image you want to see that where exactly the tumor is in the brain, okay, in that image. So same size image we need. So for that there is a need to have the something that we can, which can bring, or which can bring that image which have decreased with this the architecture of deep learning again to the same size. So for that, people that is Roner Berger in 2015 designed this unit architecture. Okay, especially they have designed it for biomedical image segmentation, and they have shown the result on skin cancer data set. Okay, with this, so what it is doing, so here they are performing the convolution operation. Okay, then they are doing the downsampling. Okay, means reducing the size of the image and extracting the features. See here up to 1024. Okay, the image, you can see that this is up to which they have reduced the image. So now from here they started upsampling it. Okay, from green, just see on the right hand side, they started increasing the size by taking the information from the previous layers. Okay, every time they are taking the information from the previous layer, and this is, you can even say, the one phase on the left hand side, you can say it is an encoding part, and on the right hand side it is your decoding part, or you can even say downsampling and upsampling. Okay, so finally the result whatever you will get, that is so mostly similar or mostly close to the input size image. Okay, here you can see it is 572 cross 572, but here it is 388 cross 388. Okay, there is somewhat little surge in the size of the image. Okay, so now that model was designed for just 2D images. Okay, so, but as we are saying, if you are taking the image of, let's say, the brain, it is a 3D. Okay, it is having a 3D structure. So that we cannot do with this 2D. Okay, that is a 2D unit because it is specially designed for your 2D images. So for that, the same author, along with their other colleagues, they have designed the 3D unit. Okay, so what they did in this architecture, they replaced all 2D operation with 3D counterparts. Okay, same thing is there, just they replaced with 3D counterparts. And here in this case, you can see that two different images are there. A part in this figure, A part is there and B part is there. Okay, so first is your raw image. Okay, whatever image is there. Okay, this is just a medical image, raw image is there, and on this raw image, what you can do, you can perform the manual sparse annotation. Means you can give that this is some set of pixels, you can give that this belongs to the region which we want. Okay, let's say a tumor, then you can just find out some set of points that belongs to the tumor region. Okay, and then you can train and apply 3D units, so that whatever pixels you are having, that this is your let's say the pixel which belongs to tumor. So what it will do, it will analyze the other pixels which are surrounded by it, and then on the basis of that, okay, information, that you can get the segmentation result. So this is a manual annotation, means you can do it manually as well, and you can also do it, you can directly do it without manually, means automatically also you can do it. Whatever means in automatic, what is there, you will have already the trained model. Okay, with the help of trained model, you just have to give the input image, and then you can perform the segmentation task. Okay, so in both the cases, this is beneficial. So as we have seen that there is unit architecture and 3D unit. Okay, all are related to your segmentation, because if we want to find out the reason, okay, of particular disease, so these are related to that. Now next is your adversarial, means generative adversarial network. So basically these are also people started using it, or otherwise it has been used in the other application area of computer vision, but now in medical images people started using it, and have seen the papers which are mainly related to the skin cancer or histopathology images. Okay, that is the breast cancer and all those. So in that areas people started using it, and why they are using it, the main reason is that we are saying in the challenge, in the previous slide we have seen that what are the challenges. Okay, so in challenges we have seen that challenge is the rarity of your data set. Okay, that is the biggest challenge. So if we are not having the data, then what is that main thing? So we need to have a data set. So for that, we should, if we are not getting it from the hospital, the data set, what we have to do, we should generate it. Okay, so people started generating synthetic data set. Okay, so in generative adversarial network is basically having two different parts. Okay, that is a generator and a discriminator. So generator, what it is doing, it is learning, it learned to generate a plausible data, means data which you can say that yes it is, you cannot say that it is not a real data. Okay, that is a plausible data it will generate, and generated instance become negative training sample for the discriminator. Means negative means obviously not a, okay, that is a fake images, so it will work as a negative training example for your discriminator. And what is the aim of your discriminator? So what it will do, it will learn to distinguish the generator's fake data from the real data. Okay, and discriminator penalize the generator for producing implausible results. Okay, let's see here in this case, here there we are having a generator. Okay, so how it will generate your uh, synthetic images? Okay, suppose we are not having the, we are, skin cancer data set size is very less, we want to increase the size of the data. Okay, so what it is doing, so here generator, so it will take some random noise. Okay, it can be of anything, and based on the model, this is a deep learning model which we have to design according to the requirement. Okay, as we are saying, we want to generate skin cancer image, so based on that, this deep learning model need to be designed. Okay, then it will generate some fake result. At first may be possible that it is not able to give the exact skin cancer type image because it is generated from noise, so maybe something wrong it will give. So what it will do, discriminator will tell that this is a fake image. If it is not good, then it will directly say that it is also a deep learning model, that this, the result which generated by the generator is fake. Okay, so now based on that information, generator will again train itself. Okay, and generate the again one more image, and it will give it to discriminator, and it will do it till it will not, till discriminator is not able to find out that whether the fake image is real or not. Okay, so likewise data is generated. Okay, discriminator just use the training data set for identifying the difference between the real and fake images. So this is just a generative adversarial network whose aim is to generate a synthetic data. Okay, so is it clear up to here? Am I audible?
Yes, ma'am, you are audible.
Okay. So now next is the segmentation based application. As we have seen different models, okay, that is deep learning models. So what are the applications related to the segmentation? So applications can be multi-organ segmentation. For example, someone has taken the problem in stomach. So what they do, they will take the CT scan or MRI scan of your full stomach, okay, full stomach region area. So in that case, if you want to find out that what is the organ which is related to stomach, which is here related to your liver, etc. So in that case, it is having the advantage. Okay, like tumor segmentation, stroke segmentation, basically related to the brain. Okay, cancer detection, lung disease detection, and diabetic retinopathy detection, etc. And whatever data set I have shown in the previous, okay, from there you can find out that in which area you want to work on, and those are just related to the application areas where you can apply these deep learning methods. Okay, So just see, this is just an example. So this is a CT image from ABD 110 dataset. Okay, and this is just a recent publication, okay, by Tang et al. In 2021. So here in the left hand side you can see that these are the ground truth information, means which are annotated by the doctors or the medical expert, that this region belongs to the spinal cord, this region belongs to your that is the large bowel, this region belongs to the stomach, this blue region belongs to your liver, etc. And these are the results which they have obtained, that is the author have obtained by using the spatial context of a self-attention model. Okay, so and these are just the contours. Okay, that is the boundary of the segmented region. So these are just the multi-organ segmentation example. So this is the model what which they have used. Okay, till now we have seen that either we are using 2D unit, okay, that is just a unit, or either if we want to work for a 3D images, then we are going to use for 3D unit, okay, or its variants. Okay, you can design its variants depending upon the application. So in this method what they have done, they have used both 3D unit and a unit approach. Okay, both. Here you can see the downside, it is a U-shaped structure. Okay, because of this U-shaped structure, they have given the name of the model as that is the unit. Ronsberger, they have given the name as unit because of just a U-shaped structure. Now here in this case, this model consists of your 3D context feature encoder. Okay, here in this case on the top, and your 2D decoder and a multi-slice feature aggregation module. Okay, that is which is based for fusing the, which is just for fusing 2D features and your 3D features. Okay, so what they are doing in this case, this is for example the CT scan of your stomach. Okay, the stomach region area. So they are just taking one slice of that, because if you are taking a CT scan image, it will have more than, let's say, 100 slices are there, okay, for his stomach region. So they are taking one slice, and on each and every slice they are finding out the region, okay, different regions in your that area. So these are just here first they are performing the encoding and then decoding. Okay, and they are also using this 3D feature also. On the top side you can just see they are downsampling the image 3D, and they are performing the 3D unit operations. Here means 3D convolutions they are doing. Okay, and finally when you want to generate the final image, that is on the right hand side. Okay, so there you incorporating the last, okay, that is upsampling they have done, and the features from the last layer of your 3D convolution. So on the basis of that information of both, that is 3D and 2D, they are finding out the complete region, that where exactly the stomach is there, where is your spine, where is the liver region. Okay, so the other one is the tumor segmentation application also people are using. So this is just the other model. Okay, here this model is using both 3D and 2D concept. Okay, both concept they are using. Now in this case, the other concept which has been used in tumor segmentation is GAN model. Okay, they are using generator and a discriminator. Okay. So in this model, they have used this concept for identifying tumor from different modalities. Okay, like people are having the same patient can have the different modality images. For, let's say, there is a tumor, it can go for CT scan as well as your MRI scan. Okay, so from both the modalities you want to find out that where exactly the location of your tumor and how the its shape is. So they have used the concept of both generator and discriminator. So what they did, for example, there is a modality A. Okay, generator will generate the modality B data. From CT image data they will try to find out the MRI data. Okay, so means different modality data they will generate, and discriminator will tell whether the generated data is right or wrong. Okay, once it is done that it is able to find out that the generated data is true, means you are making fool of the discriminator. If that is the stage, then you can take the parameters, you can transfer the parameters, and on those parameters you can perform the single prediction. That is, from just a CT scan you can find out that there is a problem. And likewise for the modalities B, like for a modality B is generating a modality A data. Okay, means the images of different modality, and again you are transferring. So in both of the places you can perform a single modality prediction as well as a multi modality prediction. Okay, that is, let's say from CT scan also you can find out where is the tumor region, and from MRI as well, and from the multimodality prediction also you can take out both the features from both of the trained models, and you can find out that where exactly the problem is. So this is just the example or the model which they have created, and these are just the ground truth, the information. Here you can see the MRI image and different images available. So this is just the MRI image. Okay, so and here you can see that these are the results obtained by them. Okay, at the first row, that is results obtained by them and the ground truth information. So here you can just say that the accuracy what they have obtained was just you can say 79%. Okay, they have just shown the result on the best uh, image. Okay, so but overall their accuracy was not that good, means there is a chance that we can even uh, modify the model and can improve the accuracy. Okay, and basically they have used the breadth 2017 and breadth 2018 data set. Okay, so this data set can be used for the research work, which contain T1, T2 and flare images. Okay, and the other application area is the heart segmentation. Okay, so this is just a snapshot I have taken from the recent paper published in 2021. All whatever I have taken is that from the recent publications only. Okay, because what is research going on right now, that is the main focus. So here uh, as you can see, sign boundaries are there, contour is there here in this case. So basically these are just a heart region. If sign is there, means this is the manual segmentation done by the medical expert. Okay, but the author is able to find out that this yellow boundary is showing that this is a heart region, but no, this is not a heart region. Heart region is only indicated by this, that is sign line. So here you can see that how inaccurate the author is giving the result, that is for volumetric heart segmentation. So here there is a chance that we can improve the segmentation result. Okay, so approach can be designed here for this kind. The other application area in case of segmentation is skin cancer segmentation. Okay, let's say this is on the top side, you can see two images are there for skin cancer images, and there is a repository for skin cancer segmentation, that is ISIC. Okay. From there you can find out or you can download the data set and you can work on. Every year they are giving the data set and organizing the competition, and you can find out from the grand challenge. Okay, the whatever website I have told, from there you can find and you can download the data set. They have provided previous data sets are also there available, and they are freely available, so you can download and work on them. So now here for skin cancer segmentation, this is just architecture taken from the recently published paper from neurocomputing in 2022, this year only. So they have designed a DNet architecture. Okay, so basically its encoder use the ResNet 15 and its decoder consists of 5 convolutional blocks. Okay. So now here, as we say, scan image is there, then they are performing the convolution operations and pooling operations, then RELU, that is thresholding operation, obviously. Okay. So now from here, they have performed the encoding part. Okay, means they have reduced the size of the image, and now you want to increase the size of the image based on the features, okay, of this cancer region. Okay, now it will start decoding it. Okay, means upsampling, they are performing the upsampling at every stage. Okay, taking the information from the previous layers. Okay, so that their size can be retained. So now this is just the final, you'll get the result which shows that there is the cancer, this is the cancer region present in the image. So these are some of the results which they have obtained on PH2 dataset. That is the dice coefficient, which is mostly the most important criteria in segmentation in order to find out that how accurate your methodology is. Okay, so they have obtained 0.9486 dice coefficient. Means there is a, you can, if you want to work on, you can improve the methodology, and you can, there is a chance you can improve it. And on ISIC 2017 data set, they have obtained the dice has 0.8792. Okay, means that there is a heavy chance that you can work in this data set, and you can improve the methodology. Okay, so these are just, and the other one is your COVID-19 lung infection detection. As we know, that RT-PCR.
Ma'am, what are these
for
metrics?
that?
Ma'am, I have a doubt. What are the metrics? Dice set, P. What? How do you calculate that? P accuracy.
The formula for yes, yes, I will show you the formula for them. Okay, these are just dice coefficient, Jacquard coefficient. Then this is the accuracy. This is sensitivity. This is specificity.
Okay, okay.
Okay.
Sensitivity, specificity,
So
we
these
know.
are just the measures.
Dice and JNC are new.
Yeah. Horse drop distance are also there. One criteria means they have not used it, but that can also be used for calculating the similarity between the ground truth and the obtained result. Okay, basically how we are calculating the similarity between two segmentation result. One is the ground truth. Let's say this is the here there is a sign line is there. This is the ground truth information, and yellow one is showing you the that is the result obtained by the author. So how they are finding out that how accurate their result is? They are just checking the area overlap between these two regions. Okay, more the area overlap, more the accurate result you are having. Okay, so that is there. So in RT-PCR, as we are saying, in COVID detection, we are just able to identify whether person is having a COVID-19 or not. It is affected by the virus or not. But if we want to, if a person is having the serious problem related to that infection, okay, then you need to visualize the its lung, okay, that where exactly the problem exists. So for that, people can go for CT scan or MRI scan, or even for an X-ray. That how much they can see that these are the reason where exactly the there is infection in your lung. Okay. So with the help of these methods, also the segmentation method, we can find out that this is the region affected by the infection. So here the arrow here this paper is also of recent, that is a medical image analysis. This is a very good journal of elsewhere and published in 2021. So the arrow sign is just showing you that the author is able to achieve good result on these regions as compared to the others. Okay, so basically on the ground truth, you can just see these are just a region affected by the COVID-19. Okay, means virus, affected by the virus. Now, and all the columns in different, that is the NCOV, net, and the CE net, UNet, U square net is different variants. So they are just identifying that where exactly the problem exists. Okay. So means we can design and we can work on this area as well of finding out the reason. The other one application area is your diabetic retinopathy. Okay, this in India, people have designed the data, means they have collected the images and prepared their own data set. So you can see here, one is Indian diabetic retinopathy image data set. Okay, IDRID, and many people around the world are using this data set and are trying to provide the better results as compared to others. Okay, other one is your Drishti GS, which is collected by IIT Hyderabad, and these are freely available. Okay, you can use this data set and find out the result. So what are what we can do in this case? This is just again, that is the image taken from 2021 paper, that is they have used DRNet. Okay, they have designed their own deep learning model, different convolution layers. Okay, different way to organize those things. Okay, different layers, how many kernel size they are taking, so that depend on the architecture, that what you are using and also what you are designing. If you are not don't want to use the already existing pre-trained model, that is LXNet, GoogleNet, and there are many are there. Okay, mobile net have also come. Okay, net is also there. They all have come. Okay, so these are just a pre-trained model. If you want to use them, then you can just perform the transfer learning and then find out the result. But in case of medical imaging, those are not giving good result. The reason is that they are not pre-trained on a medical data. They are trained on a MNIST data set. Okay, those are having the 1,000 category of different things, but those does not contain your medical data. So therefore it is not recommended to use the pre-trained model in these cases. Okay, but somewhere you can use it if you want to use. Okay, some results you can get, but not the exact what we want. So this in this area, what are the application is that you can find out the optical disc. Okay, so this is just the arrow on the top, you can just see this is the optical disc. If you want to find out, so you can find out that. Okay, this is the data set. And if you want to find out the fovea, here you can just see on the right hand side that this is just a fovea. So from this retinopathy image, you can find out that where the fovea exists in your let's say retina image. Okay, and the other one is you can even say these are the light regions you can just see here. Okay, let's me see here, these are the region. Okay, this region. So what is basically this? If you want to find out, so basically these are the regions which are present on the patients who are having diabetes. Okay, so or there can be one of the application area can be you are going to find out that whether there is an aneurysm in the brain, in your blood vessels in your eye. Okay, aneurysm means when brain or let's say when the blood collected in your vessels, so its size will grow. So that can you can even find out. And this region also you can find out that these are just the uh, liquid present in the eye. So these are just the applications areas which you can work on. Okay, and these are just the similarity metrics. As I am mentioned about Jacquard coefficient, there is also a Hausdorff distance is also there. These are just for finding out the distance between, just for overlapping. So if for that, for you, for example, you want to find out, you know that you have the ground truth and you are also having the result with you. So you can generate a false negative and true negative. So based on the formula of Dice coefficient, that is it is 2 multiplied by true positive divided by false positive plus true positive plus false negative. Okay, this is just a formula in terms of true positive and false positive and all those things. Okay, but basically it is just an overlap between two regions. Okay, So likewise, sensitivity you can compute with this, that is true positive, then divided by true positive false negative, and specificity by true negative, then true negative plus false positive, and accuracy is this. Okay. So these are just a similarity measure in terms of your segmentation. Okay. So now let's, as we have seen that you want to find out the reason we go for the segmentation. Now we want to categorize whether the person is having a problem or not, or what kind of again the application areas are again the same areas, but we have talked about the segmentation, that is cancer classification. Cancer can be from any kind of cancer, okay, it can be a skin cancer, it can be a breast cancer, it can be of anything, okay, lung cancer or etc etc. So these are just like diabetic retinopathy classification. You want to find out whether the retina is normal or abnormal, or let's say, as I have told you, whether the retina, whatever image we are having, retinopathy image we are having, whether that is having a hemorrhages, aneurysm, or something is there, or there is let's say hard exudates. So these just light region which is shown here on the diabetic retina, these are hard exudates. Okay, so these are just your lipid or the protein materials.
From March 28.
Hello. Hello.
Anjali ma'am, are you there? Dear participants, I think because of some of the technical issue, ma'am might have left. Let's wait.
Okay, okay. Yeah, we'll wait.
again, sorry for the interruption. Uh, so, I have told this GAN model. Hello.
No, ma'am. No, ma'am. No, ma'am. Ma'am, GAN model you have not told, ma'am, but you
Okay.
are audible.
Okay, I have it. So here in the classification, what is that? This is just a image or the taken from 2020 paper. Okay, that is the model proposed by Quinn et al. So this is basically on the skin cancer classification. Okay, so you are having the dermoscopy images. So how GAN is being used here? How they have used it? So they have taken the images. Okay, dermoscopic images, and they are using the generator. Okay, their generator is generating a synthetic data from the noise. Okay, and with the help of discriminator, it is able to generate the images which look like your real image. Okay, so here in this case, you will continue to generate synthetic image until and unless you will have the image which look like your real image. Once that is done, those images, whatever training images you are having along with the synthetic image, you can give it to the uh, classifier, means your next model. And they have used the pre-trained ResNet 50 model. Okay, they're fine tuning and performing the deep transfer learning, means there you are going to use both real and a synthetic image, both type of images you are going to use, and perform the classification into the various categories. As I have told, there can be the carcinoma, basal cell carcinoma, melanoma, and many other categories are available for skin cancer classification. So based on, means you are using the GAN model for the classification. So just look at these images. So these are just the original images. Okay, and the images which are generated by GAN are shown below. Okay, so this is your input image and you are generating the output. Okay, means the GAN generated image is there. So this is the input image and you are generating the synthetic image here. So likewise, for all the images you can generate the synthetic image. Okay, so basically, if you, let's say if you want to tell to some other, just tell whether the generated image are real or a fake. So then that person is not able to predict whether that these are really a fake image or not. So means you can use them as a training images. Okay, you can train the model with these. And once for these, you also need the ground truth images as well, as you are having the ground truth images of the original image with you in the training data set. So you can use them as a ground truth image. Means you can generate the, again, the images for the GAN mod by using the GAN model. Okay, which can give you the ground truth for this. But that is a difficult task in that, in order to give the ground truth image. In case of segmentation, let's talk about segmentation. So it is very difficult to generate the segmented region area, there exactly the location of the skin cancer. But in case of classification, we don't need the region, means the region of the skin cancer, that is on, in this region there is the skin cancer. We just know that these are the positive cases or a negative case. Let's say these are having the cancer or not a cancer. Okay, so only this category labeled information we need in case of classification. So that can be supplied and the results can be obtained. So the other application area is the, means these are just not limit only up to this, there are many application areas. So one is like COVID-19, as we have seen till now, and this is the model architecture I have taken from recently published paper in pattern recognition, that is 2022. So what they have done in this one, they are just having the model, okay, deep learning architecture. So up to here orange part. So everything is same what we have seen in the AlexNet architecture, means we are having the convolution, ReLU, max pooling, okay, and all those things. So now from here you can do many things. You can, so what they have done, they are performing 4 different tasks. Task 1 for identifying that the means the whether particular region is lung, okay, means they are performing the segmentation task, as well as they are performing the classification task. Means you can perform same, means different tasks with this architecture from here. Means the parameters from this last layer you can take and give it as an input to here. Means now from here you can start performing the decoder, okay, you can use the generate the decoder model, okay, and on the basis of that you can get the lung region. And here in task 2 you can find out that where is the region which contain the disease, okay, that which region is affected by the COVID-19, okay, that is the disease part you can find out. And then other one like task 3 you can find out that whether the image which you have given, that is of a healthy patient or unhealthy patient, then that task you can do. And other task at the same time you can find out if there is a COVID or non-COVID, and it is a non-COVID disease discriminator, okay, means various tasks you can do with the architecture, okay. You just have to make sure that at which layer you have to give it to decoder, and which from which layer you have to perform the fully connected and all those things, okay. And then like this. So these are just the application areas, but these are not limited to these, okay. So now, as we have just now come to the end of this topic, okay, talk, that is the conclusion and the future scope, that what we have seen. We have seen that deep learning model can be used to identify diseases from various imaging modalities, whether it is related to your segmentation, whether it is related to the classification, okay. You want to find out the disease reason, or you want to find out whether it is having disease or what kind of disease that patient is having. And and for future what we can do is that we can design the algorithm in such a way so that we can have a better accuracy, okay, so that the you can say medical experts can use them as a tool in order to find out, okay, more accurate result and give the results to the patient in timely manner, okay, predict this disease, okay, in timely manner. And in future also you can do that mobile enabled solutions for medical devices and clinical softwares you can provide, and you can integrate them securely with the cloud infrastructure for remote diagnosis and ease of use and IoT based medical solutions. So these are just the future scope which can be done. And some of the top conferences which are in medical imaging are MICAI, and it is a medical image computing and computer assisted intervention, and its last date for submitting a paper in this is 1st March 2022. And one is that ISBI, and in India it is this year it is organized in India, okay, and its last date is 31st January 2022. And other one is the IPCAI. So basically these two are the most important, MICAI and ISBI, okay. And the other one is SPI MI, that is SPI medical imaging. And EMBC, this is also a very good conference, that is IEEE engineering in medicine and biology conference. Another one is your CARS, that is International Conference on Computer Assisted Radiology and Surgery, okay. These are like MICAI and ISBI are much better than the journals, okay, top journals. So these comes under top categories of including journals and the conferences. And thank you. I'm having this. If you have any doubt, you can even post it here on Anjali Gautam at IIITA.ac.in. If you have any doubt, I'm here.
Ma'am, already the data sets are available in the net. Okay, and so what new can be done, ma'am, using those data sets? Because I have
As I have given in the previous slides, there is something that dice coefficient is like 0.84. Okay, so what we can do, we can design a new method with so that our accuracy can be increased. Obviously, we are with the standard data set, we can do that, because if we want to do something new, then for that you need to analyze what problem you want to do in which area. Let's say you want to work on a skin cancer. Okay, so now with just an image we can find out that where is the cancer is there in your image. Okay, that there is a region boundary, so you can find out and what kind of cancer it is. But if you want to do something new, let's say you want to find out that what is the depth of the skin cancer, till which layer of the skin that cancer has goes on. Okay, so this is something new. So for that you have to go for certain meeting with the doctors, you have to take data from the doctors, and you can uh, find out that different methodology you can design based on that. Is, uh, I hope.
Excuse me, ma'am.
Yes.
Yeah, ma'am. As you told, one of the main challenge in medical imaging is like the annotation problem or getting the information, annotated data from a doctor or an expert. So, can you suggest, is there any annotation tools that's available which can help us to
Yes.
do the?
Yes. Some of the tools which are available is let's move forward. These are the tools. Okay, these are some of the tools which you can use. A best tool is that ITK Snap and your 3D slicer. Okay, so these are the best tool with which you can find out the ground truth information. Means
Yes, ma'am.
you can perform the annotation.
Yes,
Okay?
ma'am. So if we do the annotation, then also for the research, should we get an approval or this thing from an expert? Is that need to be considered? So,
But in case of medical data, everything need to be done through proper channel.
yes, ma'am. Yeah.
We cannot say that we have, because we are not a medical expert, so we actually don't know where exactly the problem is.
Yeah, that's right. That's what
It is very
exactly, ma'am.
important.
Yeah.
Man, then how can we synthesize the images, ma'am, without their approval?
Therefore, there is a standard data sets which is already having the approval. People are in medical imaging, they are using the standard data set in a vast way. They are not, if you are having the choice, if you want to work on something, then go for the standard data set, because in case of your, you want to take the data from the hospital or clinics, then for that, everything should be gone through the proper channel. Otherwise let's say you have taken this example, you have created some ground truth for the tumor region, but exactly now doctor will say, if someone have seen your paper, that this is not a ground truth, this is not an area. Okay, like in the I have shown you the heart image, like people that person have region of heart is very small and it is showing in the full region. So if you are not an expert, you cannot say that which is the exact ground truth. So
Can we get the code for this synthesized image, ma'am?
what kind of synthesized image you are talking about?
No, program for this. I mean, you have shown for skin disease, no, ma'am. Can you get the Python code for that, ma'am?
You can get Python code. I think in that, for that, Python code is available on GitHub. For that you need to, I don't know whether it is exactly there, but both if paper are published in top conferences like MICCAI and all those, they usually provide the codes. Okay, and they are freely available on GitHub.
Okay, ma'am. Okay.
Okay. what
Hello,
are
ma'am.
the parameters to measure the classification output result? For classification, there is you can use the precision, you can use the recall, you can use the accuracy, that how accurate. Let's say from 10K, let's say the testing, for testing you have taken 100 images, and from 100 images only 90, only for 90 there are correct results you have obtained. So what is your accuracy? Your accuracy will be 90 divided by 100, that is 90% accuracy is there, okay, into 100. So these are just the, or you can even go for ROC curves, that is receiver operating characteristics curve. Those are there in order to find out that how much area under the curve you are having. These are just the way. Yes, Shankar, see. Hello, yes, sir. You want to ask something? Bhagya Patil ji is asking, is it okay to use images from doctors rather than the standard data set? You can use the images, but if you want to publish it in a good journal, then they always ask you for the approval. Okay, they will always ask for the approval if you are taking images from the hospital clinics. So because there is a
Ma'am,
committee always there. Yes.
yeah, so in that case, if we get an approval from a doctor, then will it be a valid data set?
If doctor will give a approval with the ground truth, I think that is a valid. Okay.
Yeah, valid, yeah.
Otherwise,
Okay.
we will go to some council, medical council, and they will provide some certificate. And basically, if you are not working on a human, just on an image, then in that case, just a doctor approval is, I think, okay.
Yeah, okay, ma'am. Thank you so much.
Because in case of biomedical, if you are, let's say a COVID vaccine you want to test, you have designed some new COVID vaccine and you want to find out that will work good or not. So in that, full ethical approval need to be done.
Yes,
Okay.
ma'am.
Because
Thank you.
maybe it may be possible people will die with that. Okay, things like that.
Okay, ma'am.
These tools are available online and open source. We can you can use them. You can download these tools to visualize the data. Yes, Shankar ji have raised the hand. Hello.
Hello, ma'am.
Yes.
Ma'am, how can we combine statistical data and plus image data, ma'am, using deep learning?
You can combine on the fully connected layer. I have given you the example there, na? On fully connected layer, you can use that.
Okay. Ma'am, how to integrate with CNN into a deep learning?
If CNN is just a deep learning only, if you are adding more layers into that, then it will become your deep learning.
Okay, okay, ma'am. Ma'am, which method is best for diabetic retinopathy disease, ma'am?
As I have given the here, that is you, for that you have to find out that what are the recent research in that area. Okay? Like here I
Okay,
have taken one, that is this. Okay, this is just a 2021 paper, so you can try with this DRNet model.
okay, ma'am. Okay, thank you, ma'am.
Yes.
Thank you so much, ma'am. Thank you so much for your informative session.
Thank you, ma'am.
Thank you, ma'am. And I request all the participants to join at 11:30 for the session 8 from the given link in the group. Anybody? Okay, ma'am. Thank you so much, ma'am. Thank you
So
again.
much, ma'am. Thank you all the organizers.
Thank you, ma'am. Again at 11:30.